So stick diagrams can help you kind of plan your layout much more quickly than drawing out every single layer and all the overlaps. This basically doesn't need to be entirely to scale. And generally what we wind up doing is trying to draw with multiple different color pencils or something like dry erase markers on a whiteboard to get a quick idea of approximately how big a given cell might be. So, if you look at an example with a inverter, you just have a single layer of polysilicon, and then you can draw your P diffusion and your N diffusion. From the fact that there's going to be a certain well around your P diffusion. You don't necessarily need to draw that. You just know there's P diffusion, there's N diffusion, the poly has to overlap that. The P diffusion and N diffusion are going to be a certain distance away from each other based on the minimum, design rules based on P diffusion and N diffusion and the N well. So you don't necessarily need to draw every single layer, but it gives you an idea, okay, it's going to be a certain height and it's going to be a certain width. And then when we draw the 3-input NAND that we showed on the previous slide, you can just draw, okay, I need 3 different poly silicon layers, connections or overlap over the P diffusion, N diffusion. I need the contacts in certain spots and connect it all up. You can see, okay, how many metal tracks do I need in horizontal and vertical, and that will again give you a quick idea of exactly how much width and height you might need, but in a much quicker fashion than if you had to actually draw out all the layers like we had on the previous foil. So the other thing that I would like to talk about, up till now we've been talking about a lot of the transistor details. And so you have the N well, the P plus diffusion, N plus diffusion, polysilicon, all of those layers just to create the transistors. Sometimes those layers can be your most critical factor if you have a very device dominated design where you have a really complex function and you have a whole bunch of transistors. That can make be the main constraint would be your transistors in certain areas of your design. But it turns out in most designs there's large amounts of area where the transistors are not the dominant factor in how much area you need to consume. It's actually the wiring, the actual net connections between different standard cells. You can have so many connections trying to hook up outputs from one thing that need to hook up to multiple inputs of something else, that the number of metal tracks that you have available is actually your biggest constraint. So that's the other thing you need to look at, is how many wiring tracks are available, how wide, and what's the width and space between that is required for each different metal layer, and do you have enough metal tracks to get all your signals from one place to another. So you need to look at that, as well as looking at your transistor width and spacing and your polysilicon layers and etc. So I've mentioned before, obviously well spacing also comes into play here. I mentioned before that the wells need to overlap the transistors by a certain space. So in this particular process technology that we're talking about here, the wells must surround the transistors by at least 6 lambda. So there needs to be 6 lambda overlap of the well over the PMOS transistor PMOS active area, and there also needs to be 6 lambda distance between the N plus active and the well edge. So that basically requires you to have a minimum of 12 lambda distance between the edge of P plus active and your N plus active of your PMOS and NMOS transistors. So since there's 12 lambda distance, and when we were looking at the previous foil, the metal layers were saying the minimum width for the metal 1 was 4 lambda, and the minimum space between one metal 1 and another metal 1 is 4 lambda. When you look at the distance between your contact to your N plus and your contact to your P plus transistors, you'll see that if you have 12 lambda there and you need 4 lambda space to a given metal layer and 4 lambda for the metal 1 layer itself, you can fit one metal track in between your contact to your PMOS transistor and your NMOS transistor. So that particular design, if you put your PMOS and NMOS transistor exactly as close to each other as they can get, with going for the minimum height that you can possibly get, you can only fit one metal track in between. You might find out in some cases you want to allow more metal tracks than that. If you find that you're way too constrained by the number of metal tracks that you have available. And so in some cases you'll say, well, I'm willing to make my transistors a little bit taller in order to allow more metal tracks in between your PMOS and NMOS transistors. So we can use some of the information that we just talked about to try and use the stick diagrams to estimate the area that we would need. And again, we can use both the information that we have on the minimum distance between NMOS and PMOS, as well as the number of wiring tracks we would need. You can see here, or as we talked about in the previous slide, each metal layer has a minimum, or for this metal 1, the minimum width for the metal 1 is 4 lambda. Minimum space to the next metal layer is 4 lambda. So if we wanted to put two of them next to each other, we would need 4 lambda for the width of the first one, 4 lambda for the space. The next one would need 4 lambda for its width, and then 4 lambda for the space to the following one, if you had a third one. So as you put more and more metal tracks next to each other, turns out you need the width of the metal layer plus the space as being your minimum distance per track. So for these tracks, since our width minimum is 4 and our space is 4, we need at least 8 lambda for each track. So you might see in this particular cell, the minimum height that we would need as drawn would be 3 metal tracks that are going horizontal, times 8 would be a 24 lambda height. You can see in this particular case, it's actually being drawn as 40 lambda. You might say, well, why is it being drawn as 40 instead of the 24? Well, one of the other things that isn't shown in this particular stick diagram is the connections to the polysilicon layers, A, B, and C there. Keep in mind, we will have to connect to A, B, and C. So if we had a metal layer coming in, let's say if we had a metal layer coming in to connect to the first one on the left, we could use the same track that's being drawn to connect up to the two PMOS connections there, the output metal. We could use that track because it would stop just before it gets close enough to where the existing metal is, and we connect up to the leftmost. But we would need 2 additional pieces of metal to be coming in and hitting the B input and the C input. So you can see in that particular case we would have 3 pieces of metal in the center, and then the 2 pieces of metal on the top and bottom for VCC and ground. So we would actually need 5 tracks to connect up to everything that's being shown in this cell. So if we had 5 metal tracks, 2 for power and 3 for signals, that 5 times 8 would be a 40 micron or 40 lambda height. And so it would actually make a little bit more sense for this particular cell to be 40 lambda high, as we would have troubles trying to hook up to A, B, and C if we only had it 24 lambda high. So let's do one final example. If you could all try and sketch a stick diagram for a functionality that would be output Y equal A ORed with B, ORed with C, and that result NANDed with D. So the full thing is the first A or B or C NAND D. So that's called a 3O, so OR 3 AI, so ANDed with another input. And so draw the stick diagram for that, and we'll do an area estimate. I'll give you a second to draw it. I'll actually give you a second to pause, and then I'll continue in a second. So here you can see what that function would actually look like in a stick diagram. You could draw this stick diagram in a few different ways, but effectively what we wind up getting here is you can see on the bottom A, B, and C are all connected together. So A and B are kind of connected in parallel with each other to a center connection through the N plus diffusion, and then through the metal that's connected to C, and all of those are connected in effect in parallel to ground. And then you can see the result of that OR is now connected in series, because where the connection to the D polysilicon is, the other side is not connected to ground, it's connected to our output net. So the ORing function of A, B, and C is being ORed to ground. It's the output of that function is in series with the D transistor, which means it's an AND type function, and that's connected to our output Y. And on the flip side, on the top with the PMOS, the A, B, and C are all in series to the VDD, and then that series connection of A, B, and C is in parallel with the D input to VDD. And so you can see everything that was in parallel on the bottom is now in series on the top. What's in series on the bottom is in parallel on the top. And so our output Y is connected there. You can see in this particular case, we're using 1, 2, 3, 4 metal tracks. In the internal to this, we might need some additional metal tracks available in order to connect up to the polysilicon A, B, C, and D. So you might want to have 4 additional metal tracks if you want all of those to be able to come in. Actually, in this particular case, you wouldn't necessarily need 4 additional. You could have 2 of them, like A and B, could share the tracks with the existing internal metal that connects up on the bottom and the output metal. So you might just need 2 additional tracks, which would be 1, 2, 3, 4 plus 2 would be 6 additional tracks, or 6 total tracks. If you did 6 times the 8, you would want a 48 tracks high. And then the width we would have to calculate separately. If we look at the metal tracks on the width, there's 1, 2, 3, 4, 5 tracks in the width. So if we look at that, we get 5 tracks wide, 6 tracks high, 40 lambda wide, and 48 lambda high. So just to summarize, MOS transistors are stacks of basically a gate on top, a polysilicon gate, silicon dioxide, and then silicon substrate. And so MOS, metal oxide semiconductor, they electrically act as switches, so they're electrically controlled electrical switches. And we can build logic gates out of these switches by connecting them up in appropriate fashion. And in order to actually construct the integrated circuit, we need to draw various different masks to specify the layers that we want and need in order to specify the layout for those transistors and how to make the connections between transistors. And now you know everything you need to know necessary to start designing schematics and layout for a very simple chip, or very simple, at least circuits at this point. So just one note about these, the lecture material. The majority of these slides were provided by David Money Harris, and as long as we're using these for non-commercial purposes, we can use them. So not all of the slides were from David Money Harris, but quite a number of them were. So just to give acknowledgement of that.